really a stellar researcher in NLP, and with immense depth and breadth in research. So without further ado, Tejamoy, can you please introduce him, and then we can begin the lecture.
Sure, sir. Hello, Professor Tanmoy. Uh,
Hi,
so,
Tejamoy.
yeah, so let me introduce Professor Tanmoy Chakraborty to the class. So, Professor Tanmoy is a Rajiv Khemani Young Faculty Chair Professor in AI and an Associate Professor in the Department of Electrical Engineering and the School of AI at IIT Delhi, where he leads the Laboratory for Computational Social Systems. Their research group primarily focuses on building economical, adaptable, and interpretable language models. He has served as the DAAD visiting professor at MPI Saarbrücken, PECFAR visiting professor at TU Munich, and Humboldt visiting professor at TU Darmstadt. Professor Tanmay has received numerous recognitions, including the Indian National Academy of Science Young Associate, Ramanujan Fellowship, ACL 2023 Outstanding Paper Award, IJGAI 23 AI for Social Good Award, and several faculty awards from industries like Microsoft, IBM, Google, LinkedIn, JP Morgan, and Adobe. He has also authored two textbooks titled Social Network Analysis and Introduction to Large Language Models. Prior to this, Professor Tanmoy earned his PhD from IIT Kharagpur in 2015 as a Google PhD scholar, and currently he is serving as a program chair for EMNLP 25. So, without any further ado, please go ahead with your lecture. We are looking forward to it.
Thank you very much, Tejamoy. So first of all, thank you very much, sir, for inviting me. It's my real pleasure to be here today online. I hope I would give such lectures in person. Let's see, maybe in December sometime before ASCL. And thank you very much, Tejamoy, for the generous introduction. So I understand that this is basically a part of a course. So although I prepared this as a research talk, but feel free to interrupt me if at any point in time if you feel that some of the concepts are unclear or not very clear from the slides. Okay, please make it interactive because this is going to be a 1.5 hour of presentation. So um, I would also like to hear from you about some of the ask questions and concepts. All right. So as the title of the talk suggests, I'm going to talk about model downscaling. Okay, as opposed to model upscaling. Some of in today's LLM era, people have been talking about increasing the size of the models, right? And exponential growth of the model size has been observed in last 3-4 years, 5 years, right? Scaling laws like Chinchilla's law, Kaplan's law, and so many other laws suggest that if you increase the size of the model, parameter size, data set, training protocol, etc., that improves the performance in many ways. But I will basically try to convince you why this is not a sustainable solution, why people should think of small models, right? Model downscaling and so on and so forth, right? So at the end of the day, if you feel that if you're convinced by my some of my hypotheses and some of the experiments that you have done, then maybe we can think of better ways of downscaling models. So the way I present the talk, so first 10-15 minutes, I'll talk about very briefly what we do um, in the lab around economical adaptable models. And then I'll focus on one part of the work that we've been doing last 2-3 years. Okay, so that's the idea. All right. So as usual, some motivational slides. Why small models are important. Now, these are some of the statistics, right? And this is about GPT-3. All of you know GPT-3 was the first closed source model that OpenAI developed, right? Before GPT-3, all the other models were open source, right? And then GPT-3 came in 2020, and they said that they are not going to release their code, right? Code and data and other statistics. But from the paper and from other sources, we found some of the statistics about GPT-3, and these are some of the interesting statistics. So GPT-3 training consumed around 1200 megawatt hour, right? Power, which is equivalent to running the London Eye continuously for over 5 years. Okay, so these are some of the papers which support this claim. GPT-3 training consumed GPT-3 training used approximately 355 GPU years, and that time V100 was powerful GPU. So it took quite a lot V100 GPUs, which is equivalent to running 10,000 high-end gaming PCs at full load for 13 days straight. GPT-3 required approximately 700,000 liters of water, which is again equivalent to running a standard shower for 6 years non-stop. It is equivalent to filling 1.5 million water bottle, right, with 500 milliliter each. So these are some of the numbers which kind of indicate that how hungry these models are in terms of power, in terms of water, right, GPUs, and so on and so forth. But apart from these things, which actually bothers me a lot, is that today's AI research is completely dependent on GPU access, right? And all of you agree with me. And what has happened is that due to this GPU dependent research, our research world society has got divided into two components, right? One component, one sector of society have access to huge computes, right? Whereas other part of the other part of our society doesn't have access to GPUs at all, right? Forget about A100, H100, even they don't have access to V100. So therefore, I always say that AI is a science for the rich, not for the poor, right? So from 2020, 2021, we have been trying to develop models that are less hungry in terms of resource. When I say resource, it is power, it is parameter, it is data set, right, and so on and so forth. And of course, less thirsty for water. So, and we are not the first one, by the way. Although we started, 5 years back on this after transformer model was proposed, but recently, as you, you may have seen last 2-3 years, companies like Mistral, Microsoft Phi, Quen, right? These models, these companies, they propose models like Quen, Mistral, Phi, Phi 3, 3.5, even 1 billion, 2 billion models. And of course, recently GPT, OpenAI also published their GPT OSS model, right? Which is quite small. So both small and large version of OSS has been published. So it is quite clear that scaling, increasing the size of the model has certain limitations, right? And people have realized that it's not possible to increase size anymore, because if you increase the size, you need a lot of data, and people have already exhausted with data. They've already scraped data from the internet. I don't think there is any publicly available data set which is there on internet which has not been scraped. So and at the same time, industries where models needs to be deployed, but most cases industries don't have access to their in-house GPUs, right? There are startups we don't have access to GPUs and so on. There are sensitive areas, sectors like healthcare, for example, where you cannot use this closed source models, API based models, right? Because data set is sensitive. So you need to deploy these models into your platform, right? Into your computer or servers, right? So it's natural that this kind of models, small models, are needed. Now the question is, empirical results show that quite consistently, so that small models have not that kind of performance that a large model has, right? So is it possible to make these models, small models, more intelligent, more scalable, right? More less data hungry, and so on and so forth, so that you can still achieve up to certain percentage of performance that you could achieve with a larger version of the model, right? So we started working on designing small models way back, as I mentioned, way back 2020. Transformer came in 2017, and then we got to know about Transformer in 2018, 2019, and then we thought that at that time Transformer was quite big for us, right? Around 115 million parameters. Um, and then the bot came, and people said that bot is even bigger, right? It's not possible to train a bot model, right? So we need small models like tiny bot, mbot, and so on and so forth, right? Mobile bot. Transformer was quite big at that time. So we thought that let us redesign Transformer from a very different perspective. And one of my students, Subroto, and along with my master's student Tania and Professor Saumen Chakraborty, so we started thinking of Transformer from a different perspective. And the perspective was that, so we thought that can we make an analogy between the way a word moves from one layer to another layer in Transformer, and a particle moves from one spatiotemporal region to another spatiotemporal region. Okay. Now, if you can think of these layers as time. Okay, so layer one is time zero, then time one, time two, time three, and when a word moves from one layer to another layer, so the embedding changes, right? So this is equivalent to changing the representation space, which is a spatial representation of a word, right? So essentially, when a representation moves from one layer to another layer, this is equivalent to changing a spatiotemporal representation of that word. And then we also observed that when a particle moves, there are two ways you can characterize a movement of a particle. One is called diffusion process, other is called the convection process, right? And then again, if you look at the self-attention block and feed-forward block, self-attention block, every the representation of a word is dependent on the representation of other words, because you are attending to other words, right? Every word is attending to other words, and this is essentially equivalent to a diffusion process, where in diffusion, a particle's movement is determined by the movement of other particles. Now, if you look at the feed-forward network, this is position-wise feed-forward network. So that FFN is independent of other FFNs corresponding to other words. And this is same as a convection process in particle physics, where when a particle moves, convection process says that it is independent of the other particles movement. So we mapped these two concepts, and then we borrowed ideas from ordinary differential equations from particle physics. I'm not going into details of this because this is a bit outdated research now. But then when we redesigned, we also thought that this attention operation, layer-wise operations are independent of each other, right? Although the output of one layer is fed to another layer, but the operations which is happening in layer one, for example, layer two doesn't have any idea about what are the operations happening in layer one, right? So if you think of this as function, this is basically a series of functions, which is functionals, right? So we thought that can we learn these functionals, right? So we came up with a very interesting idea called time varying attention, which essentially leverages the observation of this particle dynamics, and we reduce the complexity from order of n squared to order of n, right? So so this was our first attempt in reducing the parameter size. So 115 million transformer was reduced to 40 million transformer, right? Which is like kind of 1/3 of the parameter size, with almost no accuracy drop across different benchmark data sets at that time. Okay, so that was quite interesting. So we got a speed up of 3 times compared to compared to the vanilla version of the transformer model, and then the accuracy was also quite similar with the original model. Then we started thinking of even going broader, right? So we currently in the lab, we are currently focusing on these 3 broad dimensions: economical models, adaptable models, and interpretable models, right? When I say economical, these models have less parameters, right? These models also need less data sets, and so on. I'll explain. Adaptable models, you can adapt these models to any other task quite efficiently, right? Some of you are aware of concepts like LoRa, DORA, low rank adaptation, right? PFT and stuff like that. So I will discuss some of them in the lecture. So we came up with interesting ideas about adaptable models, and then of course, interpretability is a very fancy topic these days. So we also attempted to understand some of the emerging properties of LLMs, right? For example, chain of thoughts and stuff like that. Okay, and these are funded by three articles are funded by different industries. Okay, in economical model, we basically focus on these three sub-verticals. The first one is knowledge distillation. This is the major topic of today's discussion. In knowledge distillation, the idea is that you have a teacher model, you have a student model, right? Student model distills knowledge from the teacher model, and you basically try to come up with better objective functions for the distillation, right? Model pruning, uh, some of the parameters are not that useful. So this, such as, I mean, if you look at the gigantic models, there are many parameters which are not that useful. So can we think of, chopping down some of the parameters which are not useful, right? There are different ways of doing pruning, structured pruning, unstructured pruning, and stuff like that. I'll talk about one of these pruning methods that we designed. And then model coordination. So in model coordination, so the idea is that, let's say, you have many small models, right? Let's say you have a big model of size, for example, 13 billion, or let's say 75 billion, right? A big model. And you also have small models of size, let's say 5 billion, hypothetically, right? So can we think of, let's say, taking only, let's say, 4 or 5 small models, cumulatively, you will have roughly 30 billion size, right? And can we train or teach these small models how to coordinate among each other? And if we properly teach them, that may beat the larger model in some downstream tasks, right? This is basically model orchestration, where, let's say, this is kind of a coaching, right? So let's say there's a coach which is an orchestrator which teaches all the players how to play properly in a coordinated manner and so on. Now during the actual play time, right, actual game, the coach is not available, then the players have already learned how to coordinate, so players actually play accordingly and win the game, right? This is the concept is the same here. So here we have a coordinator which teaches small models how to coordinate, and then during the test time, the coordinator is not there, but the small models have already been trained to coordinate, and then we see bigger performance or higher performance compared to a relatively bigger model. Okay, so in today's talk, I'll mostly focus on distillation and pruning, right? And then if time permits, we'll also talk about other things. Okay, this is about economical model. And the second vertical, as I mentioned, is adaptable model, right? Where, some of you know that methods like adapter, right? LoRa and bit feed, these kind of methods where, so the idea is that, the PFT methods in general can be divided into three categories. The first category is additive parameter efficient fine tuning, right, where you add some more parameters to the model, like an adapter, right, and you only train the adapter, right? You do not train the other parameters at all. The other category is selective, right, where you do not add any new parameters, but you select some of the parameters from the existing model, right, from the existing parameter set. You select some of the parameters which are important, and you only fine tune those parameters, right, for the specific task. And the third one is reparameterization, which is LoRa, DORA, etc., where you can think of low rank adaptation of your entire parameter matrix, and you then do some sort of matrix decomposition. So, in general, PFT, specifically selective PFT, remember among these three categories, additive adds more parameters, reparameterization also has a lot of computation needed for that. Selective parameterization is the easiest way, right? You just select some of the parameters from the existing pool. But the problem is, in the literature, it has been shown that selective parameterization is not that accurate, right? For example, if you look at bitfeed, the famous bitfeed paper, they showed quite interesting performance, but that is not up to the mark, right, compared to reparameterization, for example. So at the same time, full fine tuning is of course the best, because you fine tune all the parameters. But in PFT, the idea is that you do not have resources to fine tune your entire parameter set, right? So we came up with a very interesting idea, very simple and interesting idea. We call it ID3. This was just recently published in TACL. So the idea is that um, you only choose those parameters, right, based on a heuristics. All selective parameterization, selective PFT methods are heuristic based, and the heuristics is very simple. So we only look at the parameter gradient, right, of individual parameter, right, and also the magnitude. Okay, so this is our heuristics. So you basically look at the parameter gradient and the magnitude, and of course some epsilon, just to check this corner cases, right, and you only unfold those parameters based on this heuristics. Okay, so the idea is that if the parameter gradient or the magnitude of the parameters is higher, that parameter is important, right? So in all PFT technique, the idea is that you have a budget. Let's say you have a budget of 10,000, meaning you can only unfold or unmask 10,000 parameters. Okay. So what we do here, we have a scheduler which starts with a selective set of parameters based on this heuristics. Let's say top 5%, top 10% of parameters based on the heuristics. And then over the iterations, you kind of unmask other parameters, right? So this is kind of an exploitation setup where you explore the parameters which need to be fine-tuned, and then first you explore those parameters, and then if you see that the exploitation is not enough, you again explore some new set of parameters, right? So it turned out to be really effective, and of course, and we in the paper we showed that it also beats additive PFT and reparameterization techniques like LoRa and other. Although it is a selective PFT, it beats additive and reparameterization techniques as well. All right. So this was about selective parameterization. Now we also looked at we tried to understand LoRa adapter, and we realized that neither LoRa nor full fine tuning, right? None of them are are robust to hyperparameters, right? Hyperparameters like, let's say, learning rate, batch size, epoch, and so on and so forth, right? Number of epochs and so on and so forth. So if you change batch size, learning rate, so the accuracy varies quite significantly. So they are not at all robust. So can we think of redesign LoRa, right, which would be robust at the same time accurate, right? So what we did, we basically use a Bayesian formulation of LoRa, right? So as you know, in LoRa there are two important matrices. One is this down projection and then up projection, right? So for the time being, we only focus on down projection, as you see here. So this is the down projection matrix, right? And we assume that, and we what we said is that you do not need to learn the entire down projection matrix, right? What you do instead, you think of this as basically, I mean, you think of some sort of prior, right? And you initialize this LoRa parameters from some prior, right? And this prior can be, let's say, a Gaussian mixture model. Let's say a mixture of Gaussian distribution, right? So you sample parameters from the Gaussian from the mixture of Gaussian distribution, right? But what you need to train, you only need to train the parameters of this Gaussian model, Gaussian mixture model, right? What are the parameters? And if you assume that the mean is 0, then essentially the learnable parameters are the variance, right? Variance and the mixing index, right? Mixer concentration. So, and then you can also think of other prior for this learnable variance and for the mixture concentration, right? For example, in our case, we considered the Dirichlet distribution for as a prior for mixture concentration, and for learnable variance, we also considered another prior distribution. The good part about this kind of, and all of us know that generally Bayesian parameterization is always stable, right? Sometimes these methods do not yield accurate results, but they are in general stable. So we showed, and then we again did a lot of other tricks, right? For example, we did not maximize posterior. We basically focused on likelihood maximization and so on and so forth. Those things are not important, right? And then we showed that if we think of this kind of reparameterization, right, the model would not only be accurate, but also the model would have some sort of Lipschitz bound, right? What is Lipschitz bound? So the Lipschitz bound says the Lipschitz continuity Lipschitz bound says that let's say you have two embeddings, right? Let's say you have two words whose embedding space is quite close to each other, right? Now, if you feed it to the function, you think of this LLM as a function, right? The model as a function, and you look at the output of these two embeddings, right? Of these two words, and you look at the distance between these two. So distance between two embeddings in the input space and distance between two embeddings in the output space, and there should be a bound on this. The distance should be bounded by certain constant. So in general, there were studies which showed that a transformer is not Lipschitz bound at all, right? So we thought, can we think of making it more Lipschitz bound, and in that way the model would be accurate. And there is another study which I mean we also did another study around this. This is not presented here, where we showed that so in that study we call this model transject. It's not here in the slide. If you look at my paper, you'll see. So transject, in that paper, we showed that transformer is not Lipschitz bound, and transformer is not injective, not one-to-one, right? Because of this weird kind of operations like additive operations and so on and so forth. So we attempted to make it Lipschitz bound by changing things here and there, also injective. And if the model is injective, the model will have low entropy and so on and so forth. That would always be useful in terms of power, energy, and so on and so forth. I mean, you can based on this the thermodynamics laws, we know that low entropy processes needs less power, right? So we also thought of redesigning transformer for that. Anyways, so and then so these are on PFT. We also did some work on in-context adaptation. Now, this is a bit outdated work, but it's very interesting. I think I presented this work a couple of years back to the same class. Sarah invited me for that in 2023. So the idea is that, let's say you have a lot of data sets in high resource languages. Let's say English, Chinese, Spanish, etc. You have a lot of data sets, but for a low resource language setup, let's say Santali, Vili, this kind of language, you do not have any examples, right? Corner case, hypothetical case, no example. So if you do not have any example, right, to write a prompt, even a prompt, right? How do you write demonstrators so that the model understands this, right? A typical cross-lingual low resource setup. So what we did, so we came up with an idea through which we effectively sample examples from high resource languages to write prompts for low resource language. So this is cross-lingual in context learning, right? Similarly, in another paper, we showed that now think of high resource tasks, right, which are age-old tasks, like let's say machine translation, right, sentiment analysis, emotion detection, right, NLI, etc., right? And then you have some task which is low resource task for which you do not have enough data, right? So how do you write prompts for this low resource task, right? We came up with an interesting idea inspired from Multi-Arm Bandit, where right this basically this bandit chooses a task from the low resource from the high resource task, and within a task then it chooses an example, right? There's there's an optimization process throughout, and based on that for a given task, for a given unknown task, you first choose which known task or which high resource task would be useful for you, and then within that high resource task which examples would be used for you, right, to write this prompt. So this is cross task in context learning. Okay, so this was about adaptive models. Now coming to interpretability, right? So I think this was the first paper, our paper last year, where we showed how chain of thought actually works in an LLM setup, right? So some of you know, some of you are aware of this mechanistic interpretability, right? Where we essentially corrupt some of this activation, and then you do some activation patching, and you try to basically understand the neural circuits which are responsible for certain operation, right? And in case of chain of thoughts, we showed that when you write a prompt, right, there are multiple parallel circuits which are activated. Okay, and they are redundant circuits, right? So redundant neural pathways. So it means that if you somehow identify these redundant circuits, and if you remove some of them, and we showed that if we remove some of them, let's say 40% removal of this redundant circuits can still yield 90% of the accuracy, right? But we did it post hoc, right? Not pre hoc, post hoc setup. So we had this LLM, and then we probed. We did this activation patching, and then we discovered these circuits. So it means that it again hints that some of these circuits are not important. Some of the parameter chains are not important, right? We also observed that if you think of these layers, right? There is, let's say, transformer has 12 layers. Bottom 6 layers are responsible for pre-trained knowledge storage, right? So you have this pre-trained knowledge, you have next for prediction task, you gain knowledge from your pre-trained data, and the bottom 6 layers are responsible for that, whereas top 6 layers are responsible for in-context knowledge. So whatever you write in context, the top layers are responsible for processing those knowledge. So it means that when you fine-tune for a task, you should focus on top layers, not the bottom layers, right? When you think of also adding adapters, you think of top layers, not bottom layers. Okay. And one of our recent works, very recent works, we tried to investigate instruction fine-tuning. And we know that in instruction fine-tuning, what we do after pre-training, you teach the model how to follow instruction. So you have instruction data and the response data, instruction response. And generally, when you compute loss, we compute it on top of the response output, right? We just ignore the instruction tokens, right? This is kind of analogous to teaching a baby how to answer 2 questions without teaching the baby how to understand the question, right? So if you do not have loss function on top of the instruction tokens, then how does the model understand the instruction properly? But this has been the practice, by the way. Last 2-3 years, people have been just focusing on the response tokens, not the instruction tokens. So we said that we should also have some sort of loss on top of the instruction tokens, and we came up with a kind of minimax objective function where not a minimax as such, basically a weighted objective function where we have some weights for the instruction tokens, some weights for the response tokens, and we showed across bunch of models. Right? It's a huge experimental setup, bunch of models that this actually helps. So this is basically an accidental result. The reason is that we started understanding or interpreting instruction fine-tuning, and then we ended up coming up with a completely new objective function for instruction fine-tuning. Okay. All right. This is about the overall idea or overall work that we have been doing. I can take a pause if there's any question, feel free to ask, and then we move to the next part. Any question? Clarification? Okay, all right. Let's move on. But guys, please feel free to ask questions. Okay, otherwise it will become very monotonic. Okay, so let's look at the distillation process. Okay, economical model distillation process. I start from very basics, right? So distillation was first proposed by Hilton in the neuro context, right? Way back 2015, where he showed that you have teacher model, big teacher model, you have a small student model, and you have logic distribution here, you have logic distribution here, right? And what you do, you try to minimize the logic distribution, right? So you see here, this is the logic softmax, and you basically do some sort of L2 norm between two, right? And generally, teacher model is frozen. Generally, teacher model is frozen, and you only distill things from teacher to student. Okay, and the idea is that the more closer, the closer the this gap is, right? So the smaller the gap is, the higher the distillation, or the better the distillation. Okay, so later on in 2019, people said that, look, only output level, at the output level, if you look at the logic gap, that may not be enough. You also need to look at the intermediate layers. Okay, and your objective should also be to minimize the representation between intermediate layers. So this is your teacher model, your student model. Let's say this is the fifth layer of your teacher model, fifth layer of your student model, and then you minimize the gap between these two representations, right? You see here again. Let's say you think of as either as KL divergence or some sort of L2 norm and so on, right? So this is called layer wise distance, and this is called KD loss. Remember, this is called KD loss, and this is layer wise loss. Okay. So now then a series of papers were basically proposed, to think of better distillation. But most of the cases, the distillation process is unidirectional, meaning that there is always a distillation. There's always a distillation from teacher to student. Teacher is not aware of student's capacity. Student knowledge from the teacher, but the teacher is unaware of student's capability. Okay. Now think of a realistic or practical setup, right? In a classroom setup, right? In an ideal setup, a teacher should first understand the student's capability. For example, let's say if you are teaching a machine learning course to a non-computer science students versus a computer science students, right? Let's say computer science students have certain background, non-computer science students have other set of backgrounds, right? So you will teach ML to these two set of classes in two different ways, right? So this is the first idea that we incorporated into the distillation process, that the distillation should be student-centric or student-aware, right? It should not be blind. The second concept that we incorporated is that there should not be an unidirectional distillation from teacher to student, right? Teacher, sometimes, in classes we have seen that, there are smart students who ask difficult questions to teachers, and teachers may not be able to respond to those questions at that time, right? And they said that, okay, give me some time, I'll get back to you later. So there is always a notion of healthy competition between a teacher and student, right? Now, why I say healthy? The reason is that it's not a strict competition as such, right? But there is always, some sort of a game where students ask questions, and teacher also asks difficult questions, and so on and so forth. And the learning should be bidirectional, not unidirectional, right? This is the second concept that we incorporated into our distillation. The third concept that we incorporated is that, let's say, when a student learns a new concept, there should be a curriculum, right? Let's say you want to learn LLM. You first learn linear algebra, maybe a probability or statistics a little bit, right? And then machine learning, then deep learning, little bit of NLP, and then LLM, right? So there should be a curriculum, and the student model, basically, the student should follow this curriculum properly, right? So there should be a curriculum learning involved into the distillation process. So these are the three things that we incorporated into our loss function, interoperative function. And I will discuss this step by step. Okay, so we call our model MP distill. It's a meta learning paradigm, right? We have a teacher model. Now I earlier said that generally the teacher model is frozen, but if you have capacity, if you have data, task-specific data, it is always recommended that you learn or you fine-tune your teacher model on the task-specific data, right? It may not be a full fine-tuning, it can be an adapter fine-tuning or so on, but you should still fine-tune the teacher model, right? If you have capacity, otherwise, okay. So you look at here, this is the teacher-centric loss. This is the loss across, so n number of data points, and this is the loss, okay? The second step is student distillation, and this is a very standard task where you basically have a task-specific student loss, and then this is your distillation loss, KD loss, as I mentioned earlier, right? Output level logic difference, and this is the layer-wise loss, right? So you minimize everything together in the student distillation setup. Third step is very interesting, and what we did, we came up with a concept called meta teacher, right? What is a meta teacher? So a meta teacher is a stricter version of a teacher, right? So what meta teacher does, so this is a meta teacher. Meta teacher is just a two-layer perceptron, very simple two-layer feed-forward network, okay? What it does, it takes the representation from the student model, student's representation, and the teacher representation. So you are given an input, you get representation from the student model, from the teacher model, right? And what you do, what this meta teacher does, meta teacher optimizes these two different losses. Now, what are these losses? The first loss is called collaborative loss. And this is basically a collaboration between a teacher and a student, right? If you look at the loss here, this is the logic for the teacher, logic for the log logic here, teacher and student, and you basically maximize, you minimize this loss, meaning you maximize the logic, right? So it means that you are trying to improve both teacher and student. This is one loss. What is the other loss? The other loss is more for competitive loss. You look at the loss here, teacher logic minus student logic, and you essentially maximize this, meaning that you maximize the teacher logic, and minimize the student logic, right? So what does it mean? So if the meta teacher maximizes this, you basically penalize the student model and give preference to the teacher model, right? So you see, this is more of a competition. This is more of a collaboration, right? And in our objective function, we basically had some sort of weighted average or a weighted combination of this collaborative and the competitive loss. Okay. Now, what ends up happening is that if the meta teacher is trained on this weighted loss, the meta teacher will even become a stricter version of a teacher model. Okay. Now, what is the fourth? And of course, you can think of theories. For example, let's say, you can show that if the collaborative loss is lower than the competitive loss, then the expected student model would be always better than the expected teacher model. Right? You can think of fancy theories like this. Okay, so now meta teacher is ready. What is the next step? The next step is curriculum learning. So we have incorporated many things by the way. So here we incorporated the concept of the healthy competition between teacher and student, right? And now let's look at this curriculum. So curriculum learner here is again just a policy learner, and it's a feed forward. Again, it's a simple feed forward network. To think of it a two-layer perceptron, right? Now, what is the task of this curriculum learner? The task is to essentially, let's say you have a bunch of tasks, right? Now, these tasks are not your test task. It's a different task. For example, let's say you have a glue benchmark or super glue benchmark, and there are multiple tasks. All these tasks are basically your curriculum. Okay. So what this policy learner does is that this policy learner or the curriculum learner does is that it takes the student's state as the input, right? And from the bunch of tasks, from the bunch of curriculum, it basically suggests a set of curriculum for the student model. And how does this model do this? I'll tell you later. Let's first understand the entire pipeline. So the policy learner takes the student state as an input and then selects a set of tasks that the student model should consider for further fine tuning. Okay. Then what the student model do? What the student models does, the student model considers one of these recommended tasks, right, and then fine tune itself, right? So you see the loss here. This is student task specific loss, and this task is not the test task, by the way. Remember, these are the other tasks that are already there with you. Okay. So once the student model gets trained on the new task, then what you do, you now in student centric distillation, there is another data set that we consider is called the quiz data set, right? A quiz data set the quiz data set can be a subset of your training data, or it can be a separate data altogether, right? Ideally, it should be a separate data. So on the quiz data, it's small data. On the quiz data, what you do, you basically look at the representation of the student model and the representation of the meta teacher model. Okay, and then we get a reward. So you look at the performance of the meta teacher and the student, and then you look at the difference, again logic difference, and that will be your reward or penalty. Okay, and then what you do, you feed this reward or penalty through standard reinforce for updating your policy learner, curriculum learner. Okay, and this process goes on. So these are the 4 steps. Okay, and you see here, you can think of a simple binary loss or some sort of regression loss, and so on and so forth. So you can also prove that for a classification task, for example, the expected binary loss is higher than the expected real world loss, and so on. Okay, so now if you look at the performance, this is only a small snapshot of the result that I have here. The other results are available in the paper. So, but interesting fact is that, so MP distill is our method, our distillation method, and there are other distillation methods as well. You see, we considered a whole bunch of distillation methods starting from Hilton's simple KD and so on. And these are some of the tasks, right? Some of you are aware of these tasks, which are Boolean QA, COPA, right, RT, and so on. These are super glue benchmark tasks. And the result indicates the difference between the student model and the teacher model if you adopt this distillation process. For example, if you use KD, a simple KD loss, right? What would be the difference between your teacher performance and the student performance, right? So, of course, the negative numbers indicate that teacher model is better than the student, right? Lower the number, it basically indicates that the student model is gradually, moving towards the teacher model, right? You see here, this is the high, negative 13.3, but here negative 2.7, meaning this distillation is better, where the gap between teacher and student is smaller compared to this one, right? Interestingly, if you use our method, right, out of 24 tasks which are there in glue, super glue, big bench, etc., there are, of course, for all the tasks, our distillation turns out to be better than other distillations. But there are some tasks for which, if you use our distillation method, so student model performs better than a teacher model. Now, what is our teacher model? It's a 12-layer board, and student model is a 6-layer board. And all the distillation methods mostly happen or mostly take place in the encoder setup, right? Generally. Now, this is quite non-intuitive, counterintuitive, because ideally our goal is to push the student model towards the teacher model, right? But we showed that if you think of better distillation, sometimes student model can also beat a teacher model, right? And this is not overfitting. We checked her code, we checked different other probing, we did different probing, and we check this is not overfitting. So we are trying to explain why this actually happens. So let's try to understand this distillation process a bit more. Okay. Now that we understood distillation, let us explain the distillation a bit more, right? So it is known that distillation always improves the generalization ability of a student model, right? But the questions are, after KD, does the student actually imitate the teacher model or what? Right? The second question is, what are the key drivers which influence the effective KD process? Right? These are the questions that we will try to answer in the following slides. Okay, so in general, when we look at the performance of a teacher model and a student model in a let's say a math kind of benchmark, right? GSM 8K or math arithmetic, etc. We look at the final result, okay, and we check whether the results are same or not. Doesn't matter if the result is wrong, that's fine. That is still fine. But the student's result and the teacher's result should be the same. Otherwise, we can conclude that distillation is not perfect, right? So this is called agreement. If you look at here, so we tested, we took a 14 billion coin model, and then a 0.5 billion coin model at a student, 0.5, 1.5, 3, and 7, and keeping the teacher model the same. And then, this is just a snapshot of results, by the way. There are other results in the paper. And then what we did, we looked at the agreement difference. Oh, sorry, we looked at the agreement between a teacher and the student model, right? And it turned out that the agreement is, the improvement in terms of agreement is quite significant. So this blue line is the performance before. The blue line is the agreement before KD, and the red line is the agreement after KD. And if you look at the gap, right, this gap is quite significant. This gap is quite significant in case where the performance, the size difference is quite large, right? But across this, if you keep on increasing the size of the student model, you see the gap basically deteriorates, right? So it basically indicates that smaller student models get a lot of benefit during distillation, after distillation, which is also quite intuitive, right? The other aspect is called fidelity. What is fidelity? So you do not look at the final result, right? But also look at the reasoning trace. Okay, so if the reasoning trace produced by the teacher model and the student model are quite similar, then you say that maybe the student model mimics the teacher model. Okay, so how do you measure the fidelity? Very simple. You look at the embedding of the reasoning trace of the student model and the teacher model. Look at the difference of the embeddings, right? And then you see what happens, right? Here we observed that again the same trend. Smaller language models, small student models have a lot of benefit in terms of fidelity, but there is a trade-off between fidelity and accuracy or agreement. Okay, it means that there are many cases where, although the model, both the teacher model or the student model basically mimics the teacher model in terms of the final output, both the final outputs are the same, right? Both the final outputs are the same, right? You see here the outputs are the same, but the reasoning traces are different. So it means that although they are quite generalizable, but they are not, their agreement in terms of thinking ability is different. Similarly, there are cases where the reasoning traces are quite same, but the final outputs are different. By the way, there has been an increasing amount of debates where people claim that the chain of thoughts, right, or the reasoning trace that the model generates, that's not the thinking of a model, right? The thinking and the reasoning trace, they're different, right? Slightly off topic, but this is something to remember. Okay, so then we again try to understand other factors. For example, I mentioned earlier that if you have enough infrastructure, enough data set to train a teacher model, this is always beneficial, right? And we see here that these blue lines indicate the teacher model or KD, where the teacher is not trained on task specific data. Sorry, this orange lines are the teacher models which are not trained on task specific data, whereas blue lines are cases where teacher models are fine tuned, right, on task specific data. It turned out that, let's say you take a 70 billion model, teacher model, versus a 30 billion teacher model. 70 billion teacher model is a very generic, good model in terms of generic performance, whereas 30 billion teacher model is may not be generic, but let's say you fine tune a 30 billion teacher model on a specific task, right? So a fine tuned small teacher model is better than non fine tuned large teacher model. Okay, now basically it says that first level fine tuning of teacher model always helps. Okay, the second experiment that we did is basically we tried to understand the effect of noise, right? So in the logit, if you inject Gaussian noise, for example, let's say you have some Gaussian noise, and this is a parameter of the Gaussian model, and up to a certain extent, right? The model tolerates KD tolerates the noise, but suddenly you see a jump or a decrease, right? It means that up to a certain level it can tolerate, but after that it can't tolerate. The third findings is very interesting. So in distillation, there is this temperature parameter which controls the smoothness and the steepness of the curve, logit curve, right? And as we all know, if you increase the value of the temperature, you see more more homogeneous, a smooth curve, right? Uniform curve, right? So it turned out that there is a trade-off between the accuracy of a KD model versus the temperature parameter. So if you increase the temperature parameter, recall will increase, right? If you decrease the temperature parameter, precision will increase, right? So using this temperature parameter, you essentially control the precision recall trade-off of the KD method. Okay, so this is about KD. We also did some other KD techniques in case of multimodality, where our teacher model was a vision model, right? For example, stable diffusion or let's say DALI kind of model, whereas mid-journey kind of model, whereas your student model is a text model, right? So what we did there is that we did something called selective distillation, where let's say you only want to distill the image knowledge from the teacher model or a text knowledge from the teacher model, right? And how do you do that? It's a very interesting paper that's already there. Okay, any question so far before I move on to the next part? No question? All right. So let me move on to the model pruning part. Okay, and what is model pruning? So the idea behind model pruning is as follows: you have a gigantic memory, model memory, right? And in model pruning, you basically want to remove some of the parameters, right? There are two ways to do that. The first one is more of an unstructured pruning. In unstructured pruning, you identify parameters randomly not randomly, of course, based on some heuristics, but not. Yes.
Sir,
Yeah.
sorry to interrupt. Before you move
Yeah.
to the model pruning
Yeah.
section, there are some questions on
Yeah.
distillation.
Please go on. I can't see the chat, so
So
please go
I'll
on.
ask
Yeah.
on the behalf of the students.
Yeah, go on.
So the first question is that you mentioned that generally the teacher model is kept frozen.
Generally,
So what
yes.
does that mean? And when can there be cases where teacher model is also like a trainable module?
Yeah,
Because
when
usually
I
I think the
yeah.
intuition is that in distillation you will have teacher frozen and student is getting taught by the teacher. So
Yeah. So when I say that teacher model is frozen, meaning that the teacher model doesn't know about the task, right? If you think of, let's say, ChatGPT as a teacher model, ChatGPT is a model which ideally knows everything, right? You do not fine tune this kind of model for a specific task, right? So no parameter updates happening from the teacher side, right? So what you do here is that you in the distillation time, you feed an input to the teacher model, right? Teacher model produces an output, and we assume that that is an open source model, meaning that you get the representation of your input from the output layer of the teacher model, right? But there is no back propagation happening, no parameter update happening, right? So you get the logic from the teacher model, you get the logic from the student model, you measure the loss. The loss gets back propagated end to end through student, not through teacher. Okay, so this is called a frozen teacher model. And when I say task specific fine tuning of teacher model, right? Either you can, let's say, fine tune some layers of the teacher model, let's say top few layers of teacher model, or you can do some sort of adapter fine tuning, right? Lower fine tuning, right? You only fine tune because for the test task or for the task that is given to you, you may not have enough data, you have small data, and you only fine tune the adapter or some layers of the teacher model. Okay, is it clear? And it turned out that if you do this student specific, or sorry, the task specific fine tuning of teacher model, that always helps.
Okay, sir. So another question is, what happens in the case when you have multiple teacher models and a single student model? Can it make the student more smarter? And in what cases?
So that defeats the purpose, because if you have multiple teacher models, then you actually need a lot of infrastructure to do the distillation, right? Teacher model is already a big model. Okay. Generally, people do the other way around, right? What people do is that although there are papers where they consider multiple teacher models, but people do the other way around. People consider multiple student models and what teacher model, and the distillation happens in multiple ways, right? So for example, let's say hypothetically, again, I do not know whether this is a right example or not. Hypothetically, let's say you have a multilingual teacher model, and you want to essentially get monolingual student models. Let's say one model should be a specific specialized Hindi model, other student model is a specialized Bengali model, other model is a specialized Tamil model, and so on and so forth. And your teacher model is a multilingual model, right? And then how do you distill things, language specific information from teacher to student? There are works on that, and we are also working on this area. But multiple teachers can definitely, I mean, at least intuitively speaking, multiple teachers may help distillation process. Yep. But that defeats the purpose, by the way, because we are talking about low resource setup, less parameter, less infrastructure, and so on.
I see. So final questions from one of the students in the class. So you spoke about one of your methods where your student model was outperforming the teacher model
Yeah,
itself.
yeah, yeah.
So the student is asking, isn't it always the case that student model is better or equal than the teacher model?
No, not at all. In student, look, this, so the logic difference is something that you are trying to minimize, right? It will never happen. Ideally, it will never happen that that the student logic distribution is similar to the ground truth logic distribution, right? Because the teacher model is already a big model, highly capable model, and you already did one round of fine tuning of your teacher model, now, which means that the ground truth distribution and your teacher's distribution is very similar, right? So a student model never outperforms a teacher model, ideally, right? But surprisingly, in our case, we have seen that there are some cases where on some tasks it did. And we also don't have any idea why it is happening. We're investigating currently. Is it a task specific outcome, or it is something that that is happening due to our objective function, and so on and so forth? We do not have, at least I don't have any concrete answer to justify why it is happening. Okay.
Okay, sir. So that would be it, sir. You can continue with the presentation.
Okay. All right. So let's move on, and I will take some more time to discuss this model pruning. As I was saying, right, model pruning is of two types. The first is more of an unstructured pruning, where you think of this as your you think of your parameter as a matrix, right, and then you choose some of the cells from this matrix which you want to prune, right, based on some heuristics. Now, the problem with this kind of unstructured pruning is that, I mean, since this is unstructured, right, quite haphazard, random, as the sparse matrix operation that you do in the CUDA level, hardware dependency, right, hardware dependent operations, these would not be. I mean, if you do this, that may not be quite appropriate if you use this kind of unstructured pruning, right? So uh, in case of structure pruning, what we do, we have a matrix, and then we have this matrix, and then we basically slice off either the entire row or the entire column. Okay. So the task is to choose which rows are not important, which columns are not important. And if you do that, you see we have a benefit, because now we can use hardware support. We have hardware support to essentially do this kind of slicing off, reducing the dimension of the matrix and so on. Right. So structured pruning is quite standard in that way. Now, how does this structured pruning happen? So you have this original matrix, okay? You have some orthogonal matrix, right? Some orthogonal matrix here, which is not visible. Assume that you have an orthogonal operation happening here, which essentially identifies rows, right, which are not important, right? You remove those rows, and then you evaluate the performance of your pruning with respect to a calibration data, right? So you evaluate it based on the calibration data. If you see that it is not quite good, what you do, you refine your pruning process, right? And this happens. You see, this goes on and on. So pruning, evaluation based on calibration data, and refinement, right, and so on. So once you are done with your pruning, now there are literature which basically showed that after pruning, the model forgets a lot of pre-training knowledge, pre-trained knowledge, right? So what you need another level of fine-tuning. It is called recovery fine-tuning, where you try to recover some of the pre-trained knowledge which you may have forgotten during the pruning step. Okay, so you see here the pruning process is dependent on two data sets. One is the calibration data, other is the RFT data, recovery fine tuning data. But since we are talking about low resource, low data, etc., let's assume that you do not have calibration data for evaluation, right? So if you look at existing pruning methods like slice GPT, LLM pruner, layer collapse, etc., they are all dependent on this kind of calibration data, right? Uh, but as I said, over dependence on the calibration data is bad, because your pruning strategy would be completely dependent or sensitive on the calibration data. Okay, so what we thought, that can we think of a method which would be independent of any calibration data? You do not need any data set at all for pruning. Okay, the extreme case. But if you have some data set, you can still use our method, and then you further fine tune with your data set. But let's assume that for the time being that you do not have any calibration data. The other important factor, very intrinsic, salient, factor that we discovered analytically, that this orthogonal operation, orthogonal matrix that we need for pruning, right? That is an additional parameter, right? It's an additional parameter set. Orthogonal matrix. Think of an orthogonal. Think of a simple, let's say, a multi-layer perceptron, or maybe a deep neural network where which task is to determine which rows are important. So we showed analytically that if you want to if your compression ratio, what is the compression ratio? The compression ratio is, let's say you have let's say 1 million parameter in your actual model, and you want to get a 0.5 million parameter. So compression ratio is is 0.5 by 1. So if your compression ratio is greater than this, what is this? This is a dimension, hidden dimension, intermediate dimension, right? So if your compression ratio is not greater than, lower than this, lesser than this, then you end up adding more parameters to the model, okay? And which completely defeats the objective of pruning. If you end up adding more parameters to the pruning stage, then what is the point in doing pruning, right? So, and interestingly, slice GPT kind of models, they actually end up adding more parameters to the model. Okay, so what we thought is that, can we think of intrinsic measures, right, for pruning, right? And we thought that let's rely on the matrix property, that we are aware of, right? For example, there's this famous theory called the point care separation theory. Okay, and this is a corollary of the point care separation theory that we derived. So it says on a high level, what it says is that, let's say you have a weight matrix W. Weight matrix is your complete parameter matrix in our case, and you have a slicing of or a sliced off matrix W dash, right? W dash, the dimension you see n cross D and m cross D, whereas m is much lower than n. Right? Sometimes, I mean, we can play with this value of m, but W dash is a sliced off matrix of W, right? If this is the case, then the spectral range of W dash would be a subset of the spectral range of W. What is the spectral range? The singular value range. Okay. Now remember, this is not a square matrix. It's a non-square matrix. You can't do eigen decomposition. You have to do SBT. So, if this is the case, then what does it mean? It means that the subset, the sliced off matrix W dash, has a spectral range or singular value range, which is a subset of the singular value range of W. Right? It means that if in our case, let's say in our case, what is W? W is the actual matrix, and W dash is the pruned matrix, right? So if we look at the singular value of W dash and W, and if you try to minimize the distribution of singular values of W and W dash, right? This would help make W dash closer to W. Okay, a simple idea, right? And you do not need any data set for that. Okay, so we call our method PruneNet. It's a calibration dataset free structure pruning method, right? And let's see how it works. So let's assume for the time being that you apply this PruneNet on the feed-forward network, not on the attention matrix. Okay, feed-forward network. Now, feed-forward, we have an up projection matrix and down projection matrix, right? Let's assume that you're focusing on only the up projection matrix, FFN1. So our PruneNet is a policy learner. Okay, and what's our policy learner? A policy learner is again a simple feed-forward network. Okay, so what is the task of this policy learner? The task is to identify which rows in this FFN are important, or which rows in this FFN are non-important to be sliced off. Okay, so you see that FFN is the input to the policy learner. It produces a flat vector of size, number of rows, and some rows, this is not one, some rows would be, let's say 0.8, 0.9, some rows would be 0.0, 0.01, 0.001, and so on. Right? Those rows are not important. So the task of this policy learner is to basically produce this weight vector or the importance vector. Okay, let's say you get this weight vector, importance vector. You remove those rows which are not important. You get a modified FFN1. This is W dash in our case. This is W dash. Okay, And then what you do, you get the spectral distribution of this. You already have a spectral distribution for this, right? You have two distributions, continuous distribution. You measure the difference between this, let's say using KS distance or any other measure of continuous distribution difference, right? And that is going to be your reward or penalty to the policy learner. Okay, and you keep on doing things again and again up to a certain iteration. Okay. So let's say you identify some of the rows which are not important here. And remember, FFN2 is just once you identify the rows from FFN1, this is equivalent to identifying columns from FFN2, and you also remove those columns from FFN2, right? You do not need to run it again on FFN2, right? So, and you do this iteratively, okay, right? And you terminate after a certain number of iterations. Very simple idea. You do not need any data. Now, what are the benefits? The first benefit is that you need this policy learner, right, which is not that big, and this policy learner is this policy learner can be applied to the other FFN layers as well, right? You can selectively choose for which layer you need this policy learner. The second beauty of this method is that once you learn this importance matrix, importance vector, you do not need to relearn these things again. Now, in case of slice GPT and other pruning methods, what happens is that let's say you want to compress 80%, or we want to compress 20% of your parameters, right? So what you do in case of slice GPT, you run slice GPT, you identify 20% of parameters and you slice off. Then later on you realize that no, I need 30% of pruning, right? So you run it again, okay? You need to run it again. But in our case, since this importance vector is constant or fixed after the training, right? You choose some of the rows. Let's say you want to do a 10% pruning or 20% pruning, you identify rows accordingly. You want to do 30% pruning, you identify rows accordingly, and so on and so forth. You do not need to learn this again and again, right? It's a fixed process. Okay, so let's look at some of the results. We compare our PruneNet method with many other baselines, but the most competitive one was SlideGPT, right? You see here, this not only decreases the flop, right, floating point operation per second, it also increases the accuracy, right, across different data sets, right, and so on and so forth, right, with different sparsity. So 20% sparsity, this is the compression ratio, right, 25% sparsity, and so on and so forth. Now, and we applied it to two models, Llama and Phi, and you see here, it not only increases the accuracy, but also increases the throughput, which is part token number of tokens per second. Right? You see dense model with all parameters, slice GPT with a pruning method is a pruning method, and PruneNet is our method. You see that for both Llama and Phi, you can still return 73. You can have 73% better inference throughput than the original one. Okay, now what's the takeaway? The first takeaway is that the most important takeaway is that our PruneNet method is architecture agnostic. Why this architecture agnostic? Because what you need here, you just need a 2-layer perceptron. That's all. Okay, or a 3-layer perceptron as a policy learner. Okay, and then it is, and then you can apply it to any layer, right, without any calibration data. These findings seem very interesting. PruneNet can compress a 7 billion Llama with just 15 minutes by 30% achieving over. You can achieve 30%. This is an incorrect sentence, but what I'm trying to say is that it can retain 80% of the performance, zero-shot performance of Llama 7 billion, right, with 30% compression, and this compression can be done with only 15. In 15 minutes you can compress it with 1/800 GPU. Okay, I will take maybe 2 more minutes, right? Very quickly wrap up, right? So now SliceGPT, PruneNet, this is quite clear that look, pruning always decreases the performance, right? But therefore people said that after pruning you do some sort of recovery fine tuning, but nobody knows that what it would be the ideal size of the recovery fine tuning data for which you can retain certain fraction of the accuracy, right? A certain percentage of your accuracy. So can we analytically think of a dependency between the original model performance, the prune model performance, the compression ratio, and the size of the recovery fine-tuning data? Right now, why this is important? This is important because if you know the dependencies, or if you know the relations between these components, right, then you can say that, okay, let's say I want to do 10% of compression, right, or 5% of compression, and I want to retain 90% of my performance, right? What is going to be the size of the recovery fine-tuning data, right? Or in other words, you can ask that, in other ways, you can ask that, okay, I want to do 10% of compression. I have 1 million data points in my recovery fine-tuning. What is going to be my performance after pruning, and so on and so forth, right? So I'll not go into details of this. It's a very interesting paper we recently wrote. It's called Compression Laws for Large Language Model, right? What it says is that let's say L0. So L0 is the unpruned performance of the model. L is the pruned performance of the model. R is the compression ratio, pruning ratio, and D is the size of the recovery data. Right now, you see that they are related. Very interestingly, basically they are dependent through power law, right? And so if you have this kind of formula, and then we have other components like alpha, beta, p0. These are not that important. You can keep it constant, or depending on the model you can decide. But it basically says that what's going to be the performance of the prune model if we have certain ratio, compression ratio, and certain data set size. But here is the catch. The catch is you should not, or you cannot expect 90% or 95% of accuracy, right? With, let's say, 50% of pruning, right? Let's say you want 50% pruning, right? 50% compression. You still want to achieve 90% accuracy. You can't do that, even if you have, let's say, infinite size of fine-tuning data. Okay, so we came up with this idea called critical compression ratio. What is this critical compression ratio? Again, I'm not going into the theory. So the idea is that this critical compression ratio is fixed for a particular model, right? So if let's say the critical compression ratio is 30%, right? Now, if you want to compress your model with less than your critical compression ratio, right? Let's say your critical compression ratio is 30%. You want to compress 10% of your model, right? You can still achieve this with a determined or with a fixed size of recovery fine-tuning data. But if your compression ratio, if your desired compression ratio is beyond the critical compression ratio, even with infinite size of your recovery fine-tuning data, you will never be able to achieve the desired accuracy. Okay, so your compression ratio should be bounded by this critical compression ratio. Okay, that's all. So I'll skip this because I don't have time. I skip this, and that's all. Thank you very much. If you have any queries, please feel free to ask.
Thanks a lot, Tanmoy, for this wonderful and very, very substantial talk. Can you hear me, Tanmoy?
Yes.